So in the last session we have seen the atmospheric boundary layer. So the different layers due to the temperature variation. So due to the day and night temperature variation, how it varied, and now we are going to see based on the wind profile how the layers varying. So in the last class we have discussed. So in the daytime we have mixed layer or convective layer. Night time we have the stable boundary layer or nocturnal boundary layer. Above that the trapped residual layer. Then we have the nocturnal inversion layer. Then near the surface there are the surface layers. And on the top you have the entrainment and capping inversion. Everything we discussed. This for summer, winter. Then inversion, that is in the bottom side we have the cool air. In the top we have the hot air. So this cool air cannot penetrate through this hot air. So it is spreading here itself and forming the inversion layer. That is always there will be a flow from hot to cold. So cold to hot is not possible. So it is spreading here and forming the inversion layer. Then within the convective layer, what happened? Due to the surface temperature, it heats the air particle, so it is rising. As it is rising, it cools down. So temperature within this air parcel is very less. So what happened? If there is no this convective boundary layer, if it is only the free atmosphere within this troposphere, you see within the troposphere, if the convective boundary layer is not there, then the environmental lapse rate will follow these dashed lines, which is minus 6.5 degrees Celsius. But what happened? Because of this convective boundary layer and the dry air, due to the heating of as it is rising, it expands and cools down. So temperature within that it is reducing compared to the outer one. So this is the line we are getting for the dry air. So what happened? At the top of that boundary layer, so this is the temperature, but once it goes to the free atmosphere, it has to follow this temperature. Then to balance this temperature difference, there is an entrainment layer which causing the mixing between these two layers so that the temperature become balanced, that is equal to the free atmosphere. Then it follows the free atmosphere. And this for the dry air. Assume it is less than 50% moisture content it has. So here also due to the heating it will rise. As it is rising, there will be expansion and cooling, so the moisture will become, there's a condensation will happen. As there is a condensation, it will release the latent heat. So due to the latent heat release, the temperature inside this air particle will be very high. So it follows this line. So because of that, what happened? Compared to the surrounding temperature, this temperature is high. So due to the temperature difference, this air parcel keep on rise until this region, because here high temperature, here low temperature, keep on rise. Once it reaches this entrainment zone, then there is no temperature difference, so it is trapped here itself, so that we have all the flat clouds. And instead of 50%, if you consider the air parcel with 100% moisture content, here also same heating, then as it is rising, cooling, condensation, latent heat release, everything will happen. Here what will happen? Here more moisture content, then more amount of due to the condensation, more amount of latent heat. So here temperature will be very high. Okay, so here if you draw the temperature profile line, then the line will be like this for 100%. Okay, so this I said 50 less than 50%. This for 100%. So here what happened? Inside that air parcel, the temperature is very high compared to the environmental temperature. So due to the temperature difference, it is keep on rising. Even there is a temperature difference within this entrainment layer. So it penetrates the entrainment layer and forms the large clouds, cumulonimbus, anvil shaped cloud, which is causing the thunderstorm, etc. and all. So this is how the cloud formation happening. Difference between dry adiabatic and wet adiabatic. Then for day and night, how it varied we have discussed. So these are all the clouds we discussed. So for the low moisture content, there may be a low level clouds. If it is fully wet, then it will form this cumulonimbus kind of clouds. That is, this cloud also, once it reaches, for example, up to this, here temperature is high, here temperature is less, so it is keep on rising. Once the temperature is equal to the outside temperature, then it cannot further climb, so it will spread within that layer itself, so that we are getting the flat annual kind of shapes you can see here. So this may be the entrainment zone or inversion zone. Most of the clouds are formed within this height, and this big cloud you can see, it is climbed due to the more latent heat release. It is also that once there is a temperature is equal to the outside temperature, it cannot climb further, it will just spread on both sides like annual shape. And we have discussed the atmospheric boundary layer, different layers due to the wind speed. Okay, so this is due to the wind speed. Till now what we discussed is for due to the heating for the day and night. This is due to the wind speed profile, how we are classifying the different layers within the atmospheric boundary layer. So this also we discussed within the troposphere. So this is the atmospheric boundary layer. So this is the complete troposphere. So within that we have atmospheric boundary layer, and top we have the free atmosphere. So within the atmospheric boundary layer we have the mixing layer in the top and surface layer below that. The surface layer further divided into inertial sublayer, roughness sublayer. Then the roughness sublayer further divided into transition layer and airborne canopy layer. And the airborne canopy layer further divided into Z0, D and all, that is surface roughness, displacement, etc. and all. So if there is no obstacles near the ground like a building, tree, etc. and all, there is no Z0, that is there is no urban boundary layer formation. Okay, so there is no Z0, D and all. If it is there, then these two layers will be added up. Okay, so mostly we will discuss these two kind of velocity profile. One is without the obstacles, another one is with obstacles. These two profile we will discuss further. And this also we discussed, that is due to the building or forest, etc. and all, we have the canopy layer. Within that we have Z0, surface length, that is if you extrapolate that original wind profile using the logarithmic profile, then we can get the zero velocity using the logarithmic wind profile. That height is the Z0. This we have discussed, and this Z0 will vary depends upon the urban region or forest region or grassland, etc. and all. Same profile. And then how to find the Z0 we discussed, that is same velocity profile. If you write in a semi-log graph, then the 0th point will give you the Z0 height. So if you know any two height, if you know the velocity at two different altitude, you can simply join the 2 points and it will intersect with the 0 point. Then from that we can find the Z0. That's how we can find it using the semi-log. This also we have discussed. Then here we have discussed the different canopy height, also the D and Z0 value. For the sea, snow surface and all, there is no canopy, there is no obstacles. So the D, H, everything is 0. But still, due to the surface, there is flow near the surface, there will be some friction. So we will get the Z0 alone near the sea and open surface. But D and H will not be there. That is complete displacement of boundary layer. This kind of displacement of boundary layer, etc. will not be there. Only Z0 will be there. For other land, there will be a Z0, D, canopy, everything will be there. From the grass, crops, urban region, forest, everything, there will be a canopy height, H value. Then there will be a D/Z0, everything will be there. After that we discussed. Then we have the gradient height and gradient wind speed. So here what happened, if you see the velocity profile, we know due to the surface roughness, the velocity is 0, then it will keep on increasing as it is moving away from the surface. For example, here they mention 8.8 meter per second at this altitude, 10.5 meter per second at this altitude, then 11.4 meter per second, here then 13.1 meter per second. After that the velocity will be constant. Here now it will be same 13.1 meter per second. So that gradient height means the height at which the velocity is constant. Okay, so here and all it is varying 8, 10, 11, etc. and all. From this height onwards the velocity is constant, so this height is called gradient height, and velocity at this height is called gradient wind speed. Okay, so after this gradient height the velocity will be constant and the velocity is called gradient wind speed. And this gradient height and the gradient wind speed will vary depends upon the terrain. For example, this is for the flat terrain or sea, etc. If you see, there is no obstacles or etc. So there is no disturbance at all. So easily it reaches the highest speed near the ground itself, and within the short height itself it is reaching the constant speed, that is the gradient speed it is achieving. Okay, so with a less height itself it is achieving. But if you see this urban, there will be lot of low rise, high rise building, and there will be a complete displacement of velocity profile, etc. and all. So here it is taking much height to reach the constant velocity. Okay, so compared to the flat and ocean surface, urban region will have the more gradient height because of lot of disturbance and turbulence within that urban region. And normally velocity also, if you see, this is the open space, flat terrain, ocean, etc. and all. So here velocity will be normally very high, but on the urban, etc. and all, the overall the maximum velocity itself somewhat low only compared to the sea, etc. So here you can see they mention wind speed over the land, wind speed over the water. So on the land, etc., the average wind speed they mention as this 6. But on the ocean, they mention average wind speed is between 10 to 15. So on the land, due to the surface roughness, there is a lot of turbulence which is reducing the velocity on it. See, on the ocean surface there is no disturbance. Here you get the high velocity, but here lot of disturbance. That gradient wind speed will be less here. That's why they mentioned on land 6 average, here around 12 meter per second over the water. So same thing as a table, for example, I have mentioned. So this Z0 DH already we discussed. For C, etc. and all, there is no canopy height or displacement height. Only Z0 may be there, but from grassland to high-rise building, there will be a canopy height D. Everything will be there, and you see the gradient height for the ocean, snow surface and all. It is around 300 meter. Then for the agricultural crop, etc. and all, 350 meter. Then for the urban region, etc., around 450 meters. Then for the high-rise building, etc., it goes up to 600 meters. So for the ocean, within the 300 meter height itself, it is reaching the constant speed, maximum speed. But for the high-rise building, twice the height it is taking. Up at 600 meter only, it is taking the maximum velocity. And you can see gradient wind speed for the sea is around 12. And for the urban region, it is varying from 4 to 6 due to the lot of turbulence, distance, etc. So this is the gradient height and gradient wind speed. And that wind speed profile, whatever we have discussed till now, is for the neutral atmospheric conditions. Okay, there is no movement of cloud. Okay, that we discussed. But depends upon the stable and unstable, the profile will vary. So the dash line is for the neutral. And in the daytime, what will happen? There will be a lot of heating, and there will be lot of vertical movement of vertical mixing will happen. So due to the vertical mixing in the daytime, that will obstruct the velocity so that the velocity will be less as the altitude increases compared to the neutral. So this will be the unstable, that is daytime, this will be the velocity profile. So this is called the unstable boundary layer, because due to the heating there will be a lot of mixing will happen, lot of cloud formation and mixing will happen. But in the night time what will happen, the surface will be very cool during the night. Okay, so surface is very cool, so there is no movement of air parcel above and below. So due to this stable atmospheric conditions, the velocity is increasing at the night compared to the neutral. Okay, so at the night we have the stable atmosphere, during the day we have the unstable atmosphere due to the air vertical motion. So during the day velocity is less, during the night velocity is high if you take some altitudes, okay, compared to the neutral. And most of the till now whatever we discussed is the neutral one. Most of the farmers also mostly they will do it for the neutral one only. So here they have mentioned, so different laws, formulas they used to find the velocity profile, also velocity at a particular altitude. Okay, so mostly it is log law, logarithmic law and power law. And it is not like we will use the single formula throughout the height. So here they mention less than the 10 meter we are going to use the, they found this urban canopy profile is having the good agreement with the real time velocity data. And from 10 to 100 or some papers or book they mention up to 200 meter, both logarithmic law and power law, it gives the reasonable agreement with the experimental data. For example, you see this green color point is the experimental velocity data, and this blue color is for the logarithmic law, yellow is for the power law. So within that, say above this 10 and within that 100 or 200, so both power law and log law almost it is matching with the experimental value, it is giving the reasonable value. Here also you see after 10 and within that 100, black color is the experimental data, and this blue and red is the power law and log law. After that height they found the power law only matching with the experimental data. And yeah, these three laws we are going to see. So we are going to see logarithmic law, power law and canopy profile law. We will discuss for both no obstacle case, also the with obstacle case. That is, no obstacle means that formula will not have the d term. If there is an obstacle, then there will be a d term. That's how the formula will vary. And the z naught will be there, because for example C etc. we discussed, there is no h, there is no d, but z naught will be there. Okay, so even there is no obstacle, z naught term will be there in the equation, d term alone will not be there. Okay, so first we will start with the logarithmic law. So here they started with the non-neutral atmosphere, that is it can be stable or unstable. So for those kind of atmosphere with the obstacle, they have given this formula, empirical formula, so it is derived from this Monin-Obukov similarity theory. And z is the velocity at which, that is height at which we are going to find the velocity. For example, height is z, there we are measuring the velocity, so uz, which will be the unknown velocity. For that you should know u star, which is the friction velocity, then k, which is the von Karman constant, mostly it will be 0.4, then z is the height at which you are going to find the velocity, d and z naught, already we know that z naught is the surface roughness, d is the zero plane displacement, then the psi, which is the correction factor for the stability. So if it is a stable atmosphere, this is the formula for the psi. If it is an unstable atmosphere, then this is the formula. If it is neutral, then the psi is 0. Then we have L, it is like a mixing length, this is the formula. So this formula we will use it if the atmosphere is stable or unstable, okay, with the obstacles, because there is a d term. Same formula they have simplified for the no obstacles case. So no obstacles means d term alone will not be there, Okay, so here there is no d term. Here d term they removed, z naught also actually they removed, because compared to z naught is very less. For example, if you see in the table, that is z naught for the C etc. just 3 mm. Any other agricultural crop etc. if you take also, just it is 10 mm, 10 centimeter something only. So we may find, mostly we will find the velocity at particular altitude only. For example, if you are going for the high-rise building, which may be of around 60 meter, 70 meter, then we may find the velocity. One is a 10 centimeter, then 50 centimeter, like that only we will find. Okay, so compared 50 meter, this 3 centimeter is nothing. Taking only Z by L. Okay. So with stable, unstable atmospheric conditions, with the obstacle, this is the formula. Without the obstacle, no obstacles, D is removed. In this equation, Z also removed, because compared to Z it is very small. This will be the final equation. And here again U star, K, psi, L value also here they have given here. These are all the formula. So whatever we discussed in the previous slide is for the stable or unstable condition, with obstacle, without obstacle. Same thing, if you simplify it for the neutral atmosphere, then this term is 0. Okay, so here they mention, if it is neutral, then it is psi is 0. So neutral means this term will be 0. So remaining will be with the obstacles, because d term is there. Then without obstacle, the d term also will not be there. So this will be the final simplest form. So most of the paper books, every calculation, mostly they will use this formula only. U star by K, L and Z by Z naught. So maybe in the next slide I will show you how we can use this to find the velocity. Again, same, just both formula. This is no d, that means without obstacle we are using. D term is there, means with obstacle we will use. So here they mention that one problem. So they have a reference velocity 6.5 meter per second at 10 meter. Okay, so I am taking that reference height, Z reference as the 10 meter. The velocity at this altitude is the 6.5 meter per second, and they mentioned this is the flat surface. That means there is no canopy. So D is 0, but still there will be Z naught. That value they have given as a 0.03 meter, and they mentioned the von Karman constant also. With that, you have to find what is the velocity height at 80 meter using the logarithmic law. So this is the logarithmic law formula. So if there is no obstacle, there is flat surface, there is no canopy height, means D will be 0. So this will be the final formula. So I have mentioned two methods. So in the first method, what will happen? So what I have mentioned, this formula, if you apply it for this reference condition, that is this is the reference height, that is 10 meter. Okay, so reference height is 10 meter, and there the velocity is 6.5 meter per second, and K is 0.4. Z naught also they mention it is 0.03. So Z reference, Z naught, K value, U at the particular altitude, everything if you know, you can find this friction velocity. So once you know the friction velocity, then we can apply this formula to this altitude. So this time, so Z is 80 meter, Z naught is 0.03, and U star just now we found, you can substitute K is 0.4. By substituting all 4 parameters, you can find what is the UZ. This is the first procedure. Or we can simply use the ratio, that is both formula. One is at the reference height, another one is at the 80 meter height. Both formula, if you find the ratio, this common term will get cancelled. Now if you see, so this is 6.5 at the reference height. So this is 80 meter, this is 0.03, and this is 10 meter. Now if you solve, we will get the velocity at the 80 meter height, which is 8.83 meter per second using the logarithmic law. So this is how at which altitude you want to find the velocity, you can find it. Okay, so you should know just what is the initial reference height and its velocity. For example, it should be about 10 meter, maybe 15 meter, 20 meter, somewhere. You have to find the velocity. With that, using this formula, you can find other altitude formulas. At 40 meter, what is the velocity? At 80 meter, what is the velocity? What is the velocity? Like that, using this formula, we can keep on find if you know the reference velocity at a particular height. That is the application. Then power law. This is the most used formula. Again, velocity at two different ratio is equal to that height ratio power alpha. That is, alpha is the power law exponent. For example, here they mention, so this is the Z1, this is the Z2. In these two altitude, we have the velocity. Here we have the velocity u Z2, here we have u Z1. So they are taking this u Z2 as a reference condition. Obviously it should be above 10 meter. So 10 meter, if you are finding the same velocity, assume 6.5 meter per second. Using that, we are going to find the velocity at 80 meter per second. Okay, so formula is different but same approach. And this alpha formula, it is 0.12 into Z0 plus 0.18. So this alpha will vary, depends upon the surface roughness. Okay, so we know different Z0 value. For C it is 3 centimeter, and for the agricultural it is 10 centimeter, like that. If you know the value, substitute, you will get different alpha value. For the C, for the flat surface, for the suburban, for the tall city center, etc. and all, depends upon the Z0, we are getting different alpha. You have to substitute here. So our aim is to find the unknown velocity at the Z1. So keep Z1 this side. If you take this one here, so it will be velocity at the reference height. Then that is height at which we have to find the velocity, maybe 80 meter per second, 80 meter, and the reference height maybe 10 meter. The corresponding alpha, for example, flat surface means alpha value 0.15. If you substitute, you will get the velocity at that altitude. Actually, I have solved the same formula in the same problem using this power law. Same at 10 meter, velocity is 6.5 meter per second. You have to find velocity at 80 meter. We know Z0, K value, everything, and this is the formula. So U reference is 6.5 meter per second. Okay, and Z is 80, Z reference is 10, and alpha for the flat surface they mentioned 0.15. If you substitute everything, we got 8.84 meter per second. So from the log law we got 8.83, from the power law we got 8.84. So that's why they mentioned from 10 meter to 100 to 200 meter, both log law and power law almost gives the same value. Okay, so we can use that. Then urban canopy profile. So you see within that urban canopy profile, so the red color is the logarithmic profile. That is, it will extrapolate, it will go to 0 at the Z0 height. Okay, so this is for the logarithmic. And power law, if you take, it is following this line. So both are inaccurately predicting the wind profile within that urban canopy layer. So both fails. So in 2000, McDonald introduced this method, that is, he combined both modified logarithmic profile and power law profile, and he has arrived at this empirical relation. With that, he could found the velocity profile which is somewhat closer to the experimental data. So that is the urban canopy profile. So it is a combination of logarithmic profile law and power law. So what happens? This urban canopy profile, it applies logarithmic profile law above this D, zero displacement height, and power law below this D. Within using that, it is finding the approximate profile within that urban canopy layer. So we have discussed three different wind speed profile formulas. One is the urban canopy profile, which is valid within the canopy layer, and from 10 meter to 100 or 200 meter, so we can use the log law or power law. Then after the 200 meter we have to use the power law. So using these formulas we can find the velocity at particular height. And mainly where we are using these formulas in the industrial aerodynamics application means mainly in the building aerodynamics, then in the wind engineering. So if you take the high-rise building or skyscraper etc. and all, for example, if you know the flow over the bluff body, if you consider, then at a particular Reynolds number, that is at a critical Reynolds number, there will be an alternative vortex shedding. Okay, and this vortex shedding and the frequency is matching with the natural frequency of this object, then it will start vibrate, which will leads to the structural damage. Okay, so which we should not reach this critical Reynolds number to avoid the structural damage. Similarly, if you take the high-rise building or skyscraper etc. and all, we are finding velocity at different height, so that just to check whether we reach the critical Reynolds number or not. So depends upon that we are designing the cross section of that is size and shape of the skyscraper at every altitude to avoid reaching the critical Reynolds number. Okay, so if the critical Reynolds number reached only, there will be a vortex shedding and vibration damage. So we are changing this cross sectional shape, also the size, to keep Reynolds number other than the critical Reynolds number. So this is the first application in the building aerodynamics. Similarly, in the wind engineering, if you take, so wind turbine height, you see it may vary from some 50 meter to even up to 300 meter. So at every height we should know what is the velocity, because depends upon the velocity, power output will vary. Here you see this wind turbine approximate velocity will be around 5.5 or 6 meter per second. Further we are getting 2 kilowatts power output. Similarly, this wind turbine may be like a 6.3 meter per second. Power output is increased to 3 kilowatts. So as the velocity increases, power output also increased. So to design a wind turbine blade and for the installation of that wind turbine etc. and all, we need the velocity calculation at a different altitude to find the proper power output. So one is the designing of the skyscraper building. Another one is the design and installation of the wind turbine. So in these applications, we are using this formula to find the velocity. And here two examples they have mentioned, that is example using the power law formula. So in the first one, they have to find the velocity at a particular altitude Z2. What they are doing, first we need some reference height and the velocity at that reference height. So they are using a small kappa-anemometer. Using that, they are finding the velocity at this Z1. For example, we know this reference height should be above the 10 meter. Assume this velocity is just a 6.5. Okay, so like that we know what is the height, what is the velocity, and we know the velocity height at which we have to find the velocity. So in the formula we know what is Z1, V1 Z1, also Z2 we know. Then depends upon the terrain, we know what is the power exponent value also. For example, if it is a flat terrain, then it is of 0.15 value. If it is of city center, then it is of 0.36 in the previous table we have used. So similarly, depends upon the terrain, we will use the alpha. So we know V1 is Z1 is Z2 alpha etc. and all, so that we can find what is the velocity at this height. This is the first way. So here we assumed what is the alpha value. In the second method, so they are taking two reference height. One is at Z1 reference height, another one is the Z2 reference height. So again using two different kappa-anemometer, they are finding the velocity at these two reference height. Then they are substituting in this power law formula. So we know what is Z1 Z2 height, also V1 V2 velocity. From there we can find what is the power exponent law value for this terrain. Okay, then they are proceeding for the final destination where we have to find the velocity. So here we have to find the velocity at the wind turbine. So again, to use the power law formula, we should need one reference value height and velocity. So here they have taken this Z2 height as a reference value. Now you see we know what is Z2 and V2 from this kappa-anemometer. Also we found the alpha from comparing these two reference value, and we know the height at which the wind turbine is placed. From that we can find what is the velocity at this wind turbine. Like that, either alpha can be assumed or it can be found with the help of two reference values. So that's how we are finding the velocity at different height in real time. Next is the turbulent intensity and turbulent kinetic energy. So turbulent intensity is how much that is how intense the flow fluctuate in the turbulent flow. Okay, so that is any time if you find the velocity, for example 10 minute, if you are recording the velocity for a particular altitude, it will not be like a straight line. Okay, so it will be keep on fluctuating here and there. So the turbulent intensity means how intense it is fluctuating. Then the turbulent kinetic energy, that is energy available in the turbulent flow. Okay, so turbulent intensity is how intense the flow fluctuates. Turbulent kinetic energy is what is the energy available in the turbulent flow. These two we are going to see. And here I have mentioned within the atmospheric boundary layer. So this is the atmospheric boundary layer. Above that we have the free atmosphere. So within this atmospheric boundary layer, how this turbulent intensity, turbulent kinetic energy varies, here they mentioned. We know near the surface there will be lot of buildings, low rise, high rise, then trees, etc. and all. Because of that there will be mountains, etc. So there will be lot of turbulent generation, that is called mechanical turbulence generation. So the turbulent intensity, the fluctuations will be very high near the surface. Then as the altitude increases, the turbulent intensity keep on reduces. Then after that, then in the free atmosphere there is no turbulence at all. It almost like a uniform flow. Okay, so turbulent intensity, that is more fluctuation you can observe near the surface. As the height increases, turbulent intensity is keep on reduces as the height increases. Similarly, the kinetic energy also varies in the same fashion. It is more near the surface because here only we have lot of turbulence. Then as the altitude increases, turbulent kinetic energy also keep on reduces. So both turbulent intensity and turbulent kinetic energy, it is reducing with the increasing altitude. So here they have mentioned the turbulent intensity graph. You see for the very rough, like a city center, we have the very high turbulent intensity near the surface. Then as the altitude increases, it is keep on reducing. Okay, so it is keep on reducing. Similarly, if it is a very smooth surface, we have the less turbulent intensity near the surface, and that is also keep reducing as the altitude increases. Okay, this is for the turbulent intensity. Then turbulent kinetic energy or power, if you see, again more turbulence will be near the surface at some low altitude only. So we have more turbulent kinetic energy, power, etc. and all near the surface. As the altitude increases, it is decreasing. Okay, so both are following the same trend. So this is just some introduction before going for the turbulent intensity, turbulent fluctuating, the turbulent kinetic energy. So already I mentioned, if you are measuring the velocity every 1 second, we will get different velocity. That is called instantaneous velocity u. Okay, at every second. For example, this graph is measured for 10 minute. Okay, so this is the 0th minute, this is for the 10 minute. So every minute we will get different velocity. This is for the 1 minute, 2 minute, so 3 minute, 4 minute, like that. Every minute we will get for that is actually every second you will get different velocity. So that is called the instantaneous velocity. Then for the 10 minute, what is the average, that is mean velocity, we can find it. So this blue color line is the average velocity, mean velocity for this total velocity, instantaneous velocity profile, that we are marking as the u bar. Okay, so u is the instantaneous velocity, which will keep on vary. Then we can find what is the average velocity for this 10 minute, that will be u bar. Then we can find the fluctuating velocity, that is from this u bar how much the flow deviates, how much the flow fluctuates, that also we can find, that is the u dash. Okay, so at every point you can find the u at different time. That u, how much it deviates from this u bar, the difference will be the u dash. Okay, fluctuating velocity is the u dash. And again, this fluctuating velocity, it is not same. So here the magnitude is this much, and on this time second, the magnitude of the fluctuating velocity is this much, like that. It is keep on varying at every time second. So we are finding the what is the average fluctuating velocity, that is the standard deviation of the fluctuating velocity. Okay, so we have instantaneous velocity, mean horizontal velocity, then mean fluctuating velocity, that is the standard deviation of the fluctuating velocity. These three terms we have. The next one is the turbulent kinetic energy. Okay, before that is just introduction. Here only to start turbulent kinetic energy. So turbulent kinetic energy, already I mentioned, this is the energy available in the turbulent flow. So mainly we are discussing about the eddies in the turbulent flow. So we have seen in the picture, you see, due to the turbulence there are a lot of eddies. First it is of bigger size, then it is reduced to the smaller size, then it is further smaller, then it will disappear. Okay, that mechanism I think I have discussed here. So first there is a energy production. Okay, maybe there is a mountain or building something, so there is a large vortices, eddies are formed, then that will be transferred to small eddies. So there is a energy transfer from the larger eddies to the smaller eddies, that is called energy cascade. Then the smaller eddies further it will be size will be keep on reducing, and after some point it will disappear because of the viscous. The kinetic energy will be transferred to a heat, so that finally it will disappear. So initially there will be a large eddy, then there will be a energy cascade, that there will be energy transfer to small eddies, then the small eddies further it will be reduced and it will be disappear due to the viscous effect. So the kinetic energy is transferred to heat. So this is how that eddy size it is keep on reducing. So the turbulent kinetic energy means we are talking about the kinetic energy of that eddies within the turbulent flow, and we are considering for the unit mass. So normally we know kinetic energy formula of mv squared. So here we are taking the unit mass, that means this value is 1, so remaining is half v square. Okay, so turbulent kinetic energy means it is the mean kinetic energy per unit mass of the eddy in the turbulent flow. And we know in the turbulent flow we are talking about the fluctuating velocities. So this, instead of v, we are using this average fluctuating velocity, which is the standard deviation of the fluctuating velocity. So of sigma square we are using, and here they mention for 3 axes, x, y, z axis they have mentioned. Okay, so this is the turbulent kinetic energy of mv squared. M is the unit, velocity is the standard deviation of the fluctuating, that is average fluctuating velocity we have mentioned. And here they mention how that turbulent kinetic energy varies for different temperature variation, that is different time. For noon how it varies, for night, for early morning how it varies they mention. For the noon, if you take the surface temperature is very high, then there will be lot of heating and lot of vertical mixing happening. So due to that vertical mixing, the kinetic energy level will be very high during the noon. So that is called unstable boundary layer, atmospheric boundary layer. So the kinetic energy will be around 2 or 2.5, like that they mention in the some books. So overall it will be more than 1 in the scale. So during the noon, due to the rapid vertical mixing, turbulent kinetic energy is very high. Then in the early morning if you see, there is no surface heating, so there is no that vertical mixing etc. and all. There the turbulence is purely due to the mechanical driven or shear driven. So we are getting the moderate turbulent kinetic energy, that is called neutral atmosphere. So where the value falls between 0.7 to 1. Then at the night if you see, there is no vertical motion at all, so we have the very low turbulent kinetic energy, which is less than 0.7. Normally it will be 0.3, 0.5, like that. So this is how, depends upon the temperature variation day and night, the turbulent kinetic energy is changing from low to high. So this is about the turbulent kinetic energy. So next we have the turbulent intensity. So turbulent intensity formula is the ratio of standard deviation of the fluctuating velocity to the mean velocity. Again already mentioned, this shows how intense the flow fluctuates from the mean velocity. Okay, so ratio of standard deviation of the fluctuating velocity to the mean velocity. And this also if you see, so this is for the city center. Okay, so very high turbulence level. So here the turbulent intensity is very high near the surface due to the city center, due to the too much surface roughness. Then it is keep on reducing as altitude increases. Then for the residual suburban and all, the turbulent intensity is little bit reduced compared to the city center. Again, that is also keep on reducing as altitude increasing. Then for the open country, etc., flat surface, etc., then turbulent intensity is further reduced, and that is further reducing as the altitude increasing. So this is how the turbulent intensity varies for different terrain type and for different altitude. Okay, so city center more turbulent intensity, then flat surface less turbulent intensity. As altitude increases also, the turbulent intensities keep on reducing.